what a lovely turnout. I mean, what a glorious weather for a start. And then on the first meeting of the year here at Tedderfield, what a turnout. All these aeroplanes.
Great, and thanks to the Tedderfield guys. They've gone out of their way for give us a good breakfast, mowed the lawns, done everything nicely. And it's a nice away game for a change. Have it our meeting at a different airfield. Good turnout.
Well done, Neil, and well organized. Thank you. Good morning, this beautiful Saturday morning in January, the first meeting of the EAA Chapter 322, and I'm speaking to the Lestrucci brothers, Paul and Peter. And what do you think of this incredible turnout?
Absolutely amazing, and I haven't been to Tedderfield for a while, but lots of development here, and it's a beautiful facility. Looks like it's very well maintained, and it's just lovely to be here and to have been invited, and we've had a lovely cup of coffee and a biscuit already, so life couldn't be better.
And Paul, what a lovely day, and lovely to have you as the chairman of EAA South Africa. Isn't this a fantastic turnout for the first meeting of the year?
Absolutely, Ethel. I think that the guys are really, we've had quite a lot of movement also over the December period where the guys were at a bit of a loose end, and we saw lots of aeroplanes coming into breakfast fly-ins again, and it's obviously going to increase as we go into the new year. And as you say, I mean, this place is, Tedderfield looks fantastic today. There's a lot of nice aeroplanes, lovely after the rains. Our flight across from Krugersdorp this morning was fantastic. It was like in still air. It was really nice in this little puddle jumper here behind us, and it's just always a pleasure, you know. And I think today is quite action-packed. Neil Bowden does a tremendous amount of work as the chairman of Chapter 322, as well as all the EXCO guys that are involved there, Carl and Graham and all the ladies that help and things like that. And I think that, we're very fortunate in the EAA in South Africa is alive and well, and I think that we owe it to a couple of these guys as well, you know, and I think
Absolutely,
that today is going to be a good one. There's that new young aviators that is coming on stream now. Tyler Pusey, Mike and Kerry Pusey are putting it together. It looks fantastic. So we, you know, obviously to make sure that the youth in aviation is taken care of as well, because us, a couple of guys, we're looking at our logbooks and it's like 40 years ago that we started to get involved here.
We're approaching TBO.
Yeah, we're approaching TBO. It's too bloody old. You know? So yeah, it's you know, I can't think of doing anything better on a Saturday morning.
Welcome to our Chapter 322 first gathering, and should go down now a little bit. Yeah, thanks everyone for, it'll go down. Thanks everyone for attending. This is our first meeting for January. It's our first away game. It's an experiment, and I think it's a great success. We've had a good turnout here. And we must thank our hosts, Ian and Theo. Where are you, Ian? And Theo, there you are. Stand up so they can see you. Thank you. Alan over there. Thank you, Alan, organizing the breakfast and everything, and the great hospitality here at Tedderfield. And I think we'll have to do another one of these in the near future, or sometime during the year, if they'll have us back. Okay. And special guests, we've got quite a few special guests here. We had all the guys from Bubsfontein this morning fly in the microlights. That was great to see. Don't forget the International Young Eagles. It's going to be hosted at Lanseria at ExecuJet. They're going to put on a big spread for us. We need pilots, we need planes, and admin and marshal volunteers for that. That's going to be a great day. ExecuJet are going all out. Landing fees should be cancelled from Lanseria, so try and be there for that. Yeah, young aviators. So these guys have got a really exciting thing happening with young aviators. Do you want to tell us a little bit about it?
Okay, well, it's kind of just, for me, obviously, no offense to all of you guys are just a little bit older than I am, and there's a little bit of a generation gap between obviously me and you. And I kind of noticed since starting to fly with my dad a lot more, I've been to a lot of you guys' events and fly-ins and everything, and they're a lot of fun. It's just that I find they can be a little bit boring. I have no one to talk to in a sense. You guys all know each other. You've experienced your aviation careers together in a way. And it's just a little bit boring for me. So we've kind of started an age group for anyone kind of starting their aviation journey to like first commercial job. So like 16, about 30, just over 30, anyone's welcome to come. And it's kind of just so that we can start a community and build our way up so we get to know each other from a younger age. Because, I mean, back in the day, you guys didn't really communicate through cell phones or anything like that, whereas we do. And so we kind of want to start more of a community so that as we grow, we stay in contact with each other as we get older and as we move on with our aviation journeys. So it's kind of just a group to get to know each other like you guys are now, but starting from a younger age, because there's nothing, you obviously have the Young Eagles, which is a very young age group, but there's kind of nothing for the in-between, and then there's your guys group. And so we kind of trying to fill the gap for the in-between group. So that's why we're starting the Young Aviators, and for anyone that wants to join, if you have any kids that are interested, tell them to join. We have social media pages which you're welcome to go onto, follow, even our events. It's just also to part knowledge onto us because you guys have a lot of wisdom and knowledge to give to our generation.
Not everybody.
But it's just a nice way to kind of bring the generation gap closer together so that we get to know each other and you guys can depart knowledge and give us information and safety tips and like anything aviation related really. And I see there's another young girl, so if you're interested in aviation, definitely join us. But it's just for anyone that kind of is my age, a little bit older, anyone who's a student studying, come and join us because we're trying to fill that generation gap between us.
This is Alan got an award last for the end of the year, I think. This is for his promotion of EAA in South Africa and his willingness to help members in regard to South African CAA licensing issues. Thank you, Alan.
Thank you. Thank you very much. Neil.
Thank you. Pleasure.
Smile for the camera.
Mike Puzzi for restoration of the Cessna C185 ZS Sierra Killer Yankee. Well done.
Thank you.
Sorry, I didn't have a frame for it.
No, it's fine.
Will you organize? Okay, cool. Okay.
What are we doing? This? Look legendary, huh?
Theo and I built over the last 6 years. We've got 23 hours on it. We've got 2 more hours until the 25 proving flight hours are up. The CAA in the infinite wisdom told us we had to fly 40. I had a fight with the Oaks and they said we could only do 25 because it's a certified engine, and we'll wait and see when the paperwork goes in. So that's the status of that. But in the flying, so we've done a lot of interesting test flying. We've, first of all, the rate of climb. So we've done everything properly according to Van's website and their whole regime to fly properly. And we download the data from the flights after every single flight, and we've had a look at it and studied it. Now, Theo, my friend over there, is a chemical engineer, and he's hugely into the detail. And so we look at these things in immense amount of detail. Now, those of you who've flown or had an opportunity or have an RV10 will know about the tunnel heating up. And the fuel system sits in that tunnel, and it's a bit of a problem. And anyway, we can see some funny things in the data, which we're going to show you. Now, we've done this fuel talk once before at the Moth Hall. But today, what we want to do is try and do it quite quickly. So we're going to have a look at actually a fuel system and how it works. The talk is can get very technical, but we want to have a look at the effective mixture and what actually happens when you twiddle the red knob. Now, those of you who fly Rotax and so on, well, you don't have to worry too much about these things because you've got FADEX systems and so on that take care of a whole bunch of those issues for you. The next thing that we're going to talk about is pressure drop. So what happens in the fuel lines, and then the effective temperatures on your fuel system and why it is so critical. So we've got a whole bunch of experiments that we're going to do here on the table. Now, we've got a fire extinguisher there for safety so that we can put out the fire if we cause one. Okay, and then the last thing we're going to talk about is vapor pressure. And vapor pressure and the difference between Mogas and Avgas is what everybody all talks about. So we'll look at the science, what's actually going on with that. So it all starts with Bernoulli. Now you know the Bernoulli theory. So here you can see there's a fluid flow coming to a restriction, and you can see the pressure is higher on the two outside ones, and as the velocity increases, there's a pressure drop, and as it reopens up again, you have a pressure drop on the other side, and that is where the vaporization actually takes place, and it's quite important to understand that. So Bernoulli is what it's all about from a flow point of view. So this is a fuel system for an RV10, and we've got on the bottom there, we've got the fuel comes from the wings into the center portion up, it goes up to the fuel selector about 6 inches that it rises, and then comes down to the fuel filter, and then through to the fuel pump, and all of that is it's on the suction side, so that it's prone to vaporization. We'll get there in a minute. And then it rises from there another 600 millimeters up to the mechanical pump on the engine. So that's basically the design of the fuel system. Now the orange square, you can't really see the colors unfortunately, but the orange square, there is the tunnel where all of this heating from the exhaust exit underneath the tunnel, and the heat actually builds up in there. If you put your hands on it on a hot day, it gets almost hot enough to burn you. So we're looking at what is the cause of this and trying to understand it from a technical point of view and see if we can't solve the problem properly and get rid of the heat buildup. Now, in order for combustion to take place, you want to come and let's just do the first thing here. So we've got a this is an electronic ignition system. So I'm looking for my fuel. There it is. So if we give that a squirt, won't you? We're using meths. Just grab the air compressor.
That's your air induction into the cylinder.
So that's just to get it to vaporize. That's just to get it to vaporize. And now we'll see if we can get it to ignite. Okay, we'll just give it another squirt. Yeah.
Let's put it in a bit further.
Yeah. Right, there I can smell it. So there you heard the pop and off it went. Now we can do the same thing. We've got it on the video. We've got a couple of what we're trying to demonstrate here. Now we've done that in slow motion, so you could actually see the burn. Okay, the next one shows it again. Sorry. So you could see how the burn, and it isn't an explosion, it's a burn. And that's the thing that we want to have a look at. So here's the next one, and this is the genie. You do this with a brandy bottle or something when you finish with it, rub it. And
Yeah, you can't see it. Oh, there you go. There you go. There's a flame front as it burns.
so that was a nice mixture, good, slow, even burn. Now, I think we've got another one. There you can see the flame front.
And when they talk flame fronts in a cylinder, that's what happens inside your engine. Except at higher pressure, it's much faster.
Okay, now that one, I don't know if you saw it, but it was leaned. I think we do it again. Now watch here. See how it goes much more rapidly, but there's actually a bounce back. And you can see the detonation happening if you see it properly. This one you might be able to see because it's now in the dark.
The closer you get to stoichiometric mixture, the quicker the burn comes.
There you could see the bounce back as it came back. Now when you go too lean, that's effectively what's happening, and that's what you want to prevent. So that's what's happening inside the cylinder. So you get the stoichiometric mix at 15:1. Now we've put into the 10, we've put a oxygen sensor, a lambda oxygen sensor. So we can actually see when that thing shows us 1, we know we're at peak EGT and we've got burning all of the oxygen, converting all of that fuel into work, which generates more heat in the engine. So you go lean of peak, And at lean of peak, you're once again back in the safe zone, and you're able to save quite a bit of fuel. And up here, you've got to be below 75% power, and up here, you can't fly above 75% power because the air is too thin.
So it means that basically, according to Lycoming, you can actually go at lean at this altitude because you can't get more than 75% power. Your engine is quite happy to go across to lean of peak without any issues. We do it normally at 60-65% power and haven't had any issues.
Over 3,000 feet.
Sorry?
If you go under 3,000 feet, then you start going over that 75%.
Yeah.
It's got to be more than 7.
So sea level, be very careful.
Yeah, so yeah, sea level, different ball game.
As soon as you get over 75% power, you're not even trying because you'll do damage.
So the whole point, why is hot starting a problem? So temperature affects vapor pressure, and you'll see we got the graphs, and it's a logarithmic or exponential curve. And so temperature affects vapor pressure. So on a hot day, the fuel vaporizes earlier. And the minute you get vaporization in your fuel line, your pump can't cope with it, and it causes problems. So restrictions in the fuel line affect vapor pressure. That's Bernoulli. So all of those 90-degree turns and all of those turns make a huge, huge difference on setting up your fuel system. And then pressure drop is cumulative across the whole line, from the tank right up until the pump. So the minute you're starting to pump it, then it's got pressure, and the pressure drop is no longer relevant. So where's the fuel pump in your motor car? In the tank. So actually, that's where it is. So the best place to put a fuel pump is in the tank, yet we don't. So because then you've got a slight pressure on the line, you won't have vaporization, problem goes away. So the one thing, on takeoff, you've got full power, so you've got maximum suction. Now, if on a hot day, at Brits it happened, with us, a hot day, hot and high, we are high, it was very hot, 12 o'clock takeoff or something like that, and you can end up with some issues. So if you're getting the vaporization and the engine starts to stutter a little bit, if you just pull back on the power a little, you've still got power and you can fly away. As opposed to leave it fully open, maximum suction, eventually the engine could well stop. So what we've then got, and all of these things, you can come and we can do it afterwards. This is a radio control model fueling system. And we can fill the bottle with some meths and crank the handle, and you can see the vapor forming in the line. I'll run the video, and if you look here, over there, so the suction line comes in there through the restriction over here, and you can't really, unfortunately, when we looked at this yesterday, it was a little bit darker, but you'll see the bubbles actually forming after the restriction, and you can see on the screen the bubbles are actually forming there. It's opaque, whereas that side it's not, and that's the actual vaporization taking place. Now watch as it slows down. So you reduce the suction, and now they've disappeared. And what that is the fluid actually boiling, in essence.
Maybe I can just clarify a little bit there. Yeah. As your pressure
It's got to be
drops,
right close to
sorry. As the pressure drops in the line, because remember, we've got atmospheric pressure to get from your tank to your pump. Is a supply line. There's no motive force other than atmospheric pressure. That atmospheric pressure is countered by vapor pressure. As any farmer will tell you, if you pump from a river, if you pump water, it has a vapor pressure at ambient temperatures of 4 kPa, or 4 kilopascal. 100 kilopascal, 1 bar, 1 atmosphere roughly. So, 1 liter of water head is equivalent to 10 kPa, which means at 85 kPa ambient pressure that we have here, if you were to suck from a river, you could suck that water up probably about 7 meters up to the pump, and from there you can pump it. Now, a similar process is happening here, but unfortunately, fuel sits at reed vapor pressure or vapor pressure of around between 65 and 75 kPa. So all you've got available for suction from your tank, from your fuel tank, to your first pump or your first point of pressurization is about 4 kPa. And that you can lose quite easily in friction losses. And as soon as you hit vapor pressure, you start bubbling. Fuel being a multi-component mixture, your light ends will bubble off first. So what you have, and that's where the opaqueness in that line came from, it's the initial bubbles that are starting to form. And that is what then gives you an aerated mixture, which is a lower mass flow, which means you're not getting the power through to your engine, i.e. the energy content of your fuel. And I'll show you some graphs later, which I did last night, from the data that we gathered from the plane, from the tin. And it's quite clear. When you switch on the electric fuel pump, the trace is absolutely steady. As soon as you switch off the electric fuel pump, where your first point of pressurization is the mechanical pump on the engine, it now has to go past the electric fuel pump and the flow meter and the filter and everything else. All those pressure drops add up, and what you're actually pushing through is a vaporized mixture or an incipient vaporization. And you can see that in the behavior of the trace. It starts jumping around. And of course, one of my objectives with the 10 is to balance the injectors. And one of my difficulties has been to get a nice steady fuel trace. Now, to try and analyze where that came from, it all boils down to vapor pressure and not being able to get a 100% steady fuel flow because of that incipient vaporization.
So technically, thanks Theo, technically vapor pressure is defined as pressure formed by the vapor over a liquid and all of that. So that's, according to Theo. According to Ian, when the sucking pressure exceeds the vapor pressure, then it bubbles. Okay, so that's the way to think about it. When you suck, it's always on the suction side. Once you're north of the pump, it's pressurized and it actually disappears. And so temperature plays a huge role. Now this is a Hodges meter, and we've got a couple of slides, videos that'll show it. But what we do is I've taken Avgas and I've taken Mogas. And we're going to see the difference between Avgas and Mogas. We all know Avgas has a lower vapor pressure than Mogas because of the design, the lead, and all of the crap that they put in there, which causes the difference. So here we are, and I mean these are all things that you can come and we can do it here. On the left-hand side is what's happening. So I've taken, using this, to take the temperature, and that's at 22 degrees. And we then load it, so you take 2 cc's into the Hodges meter, and so that's 2 milliliters in the top there, and then you pull the Hodges meter, and it then gives you a reading, which I've then plotted on this graph here so that you can see it. And we do the same with Avgas. So Mogas is the top line there, and we go from 40 degrees to 22 degrees to 40 degrees. So as it gets hotter, the blue line is Mogas, the red line on top is Avgas. And the point of it is that it is incredibly temperature sensitive, like 2 degrees or so. If on a hot day over 35 degrees, the probability of vaporization occurring in some form is in your fuel system is pretty high on Mogas. Avgas, it'll be at 38 or something like that.
Clarify something there. In the past, our vapor pressure spec for the Highveld was equivalent to Avgas. But with fuel injection in all cars nowadays, the vapor pressure spec for Mogas has been changing, and it's been getting higher. So it's much closer to sea level Mogas vapor pressure spec. And that is why we have to be super careful if you're flying on Mogas at this altitude. You have to understand what's happening to you so that you know what measures to take to counter it if it ever surprises you. And vapor pressure is the one thing that's going to cause vapor locks. Higher vapor pressure, greater propensity for vaporization, therefore greater propensity for blocking on your pump suction, on your way to the pump for your first pressurization step.
So what you're seeing here is the Hodges test, and that's now at 40 odd degrees. So I took a double boiler and put the fuel into a double boiler, and if you actually look at it, so it was there where the red line is, and it's now there with Avgas. So it certainly does, it has exactly the same propensities, You can see the lines there, straight lines, and the two things. We can do the pool test here, and those that are interested can come and have a squiz actually here as to what is happening. So all this boils down to the curves that one needs to understand in terms of understanding your fuel system and what's going on here. And what we've done, and there you can see on the right, you can see the exponential nature of the temperature. We're plotting temperature on the one axis to vapor pressure on the other axis. And you can see on the right here.
Okay, just a quick. To follow the curves, we go from pentane, hexane, octane, and as you can see, there's a very strong relationship in terms of lower vapor pressure as you get to a higher carbon number. So pentane, very steep, vapor pressure runs away. Gasoline, being a mixture, sits down here somewhere, but when you expand it, it's still, we're looking at kPa. Gasoline sits here at 40 kPa, according to this graph, but typically, very quickly, that is 20 degrees. As we go into 35, it goes to 60 kPa. From 20 degrees at 35 kPa, 60 kPa, and you don't have to think too hard. It's going to go, you're going to reach 80 kPa very quickly, and that's the local vapor pressure. Now, that's where you start in a fuel system. Take away the pressure, let's say, of the fuel vapor. That's all you've got to play with in order to get your fuel to the pump suction. Only 10, 15 kPa, and that is why you need as little pressure drop in your suction to the pump as you can afford. Anything to avoid pressure drop is key.
Theo,
Yeah.
just a question from somebody who's had these problems at a car, very ill in Germany on that.
Yeah.
But that fuel pump you showed us, my question is, open source, why don't you just, if you do all that work, put the thing in the tank? That's it.
Chalky's actually built, the last plane that he built, he put the fuel pumps right in the wing root, not in the tank, but at the wing root, to minimize the suction. So straight out of the tank into the pump, and from there.
And they don't have to be massively high pressure at that point, because all you've got to do is boost it to be above that. So you want to boost it, that 15 kPa or something like that. So it's not like the high pressure boost pump that you need for the fuel injectors.
If you're running flooded inlet.
Yeah.
Yeah, you've got flooded inlet and minimal pressure drop so you get to the pump. That is the whole objective. Is if your pump suction is too long and too many elbows, bends, switch over valves, filters, etc. Every one of those elements is a pressure loss element. You're starting at, as I say, 85 kPa local pressure minus the vapor pressure of your fuel. Now the warmer your fuel, the vapor pressure goes up. So as you get warmer fuel on a warm day, and we'll see it later, I can show you the graphs that I did of the 10. As you get warmer fuel, that vaporization, you can see the pressure curve starting to bounce around. Switch on the fuel pump, steady fuel.
So this is Chalky. It's RV9. It's actually for sale at the moment, and he's got in the wing root here is the fuel pump. And from there he pressurizes, and then the boost pump. So he's got a secondary system that he put in there, and that means that flying Mogas in that thing is absolutely no problem at all. So, the point of this slide is, so what have we learned? a good fuel system should have the lowest pressure drop possible. So as few bends as you can put into the system, that's what you want by design. And then, yeah, and a gentle 90 degree if you're going to curve it. So pressure drop is cumulative across the whole system. So from the tank all the way through until you finally deliver it to the engine. When ambient pressure plus the pressure drop exceeds the vapor pressure of fuel, it will vaporize. And it's science, there's nothing you can do about it. So design your system or understand your system properly is what we're saying. And then vapor pressure of the fuel is determined to the fuel specification. And in South Africa, our fuel quality is actually pretty good on a global scale. It's well regulated and it's blended all in the refinery. Whereas in America, they do what's called slosh blending. So you go and buy whatever crap you want at the refinery, and you chuck your own stuff into your tanker, and while you're driving, hope that it mixes it properly. And seriously, that's what happens in the States. So a fuel pump in the tank to raise the system pressure a little bit resolves these dilemmas. And the question is, so where's the fuel pump in your car? Well, that's exactly where it is, in the tank. And then reducing the suction, so reducing the throttle, if you ever have a vaporization issue, is likely to get you some power. In a situation where you've taken off and suddenly the engine starts to quit, if you come back a little bit, some power is better than nothing. And so if you take nothing else away from here, and one day, if that ever happens to you, and you remember, come back on the power, it might save your life.
Basically, pressure drop is related to fuel velocity. So velocity squared is the big issue. So the faster the fuel has to flow through the line, the bigger the pressure drop. So velocity is the key. So the bigger you can make your suction lines to the pump, the better. Slow down that suction line velocity, that will also help tremendously.
As big as possible. As big as possible.
Yeah. Absolutely.
The graph, you just explain this graph here.
Yeah,
so
here we go. Now here we've got one that shows
so we're showing fuel flow and then pressure
drop.
And we've got diameter of the lines are different diameters of pipe.
So in other words, what we have here is say 60 liters per hour. Now if you have a 0.75 centimeter line, that's going to be your pressure drop profile for that line. Pressure drop doesn't matter, but you can see you can get much more flow for the same pressure drop. Whereas in a 0.25, this is just a straight application of Bernoulli's theorem, and square ratio of areas gives you a velocity. Your 0.25 line, literally,
below
you
10.
will hardly get 5 liters per hour and already reach 55 kPa pressure drop. Whereas on a 0.75, you can get your 60 liters and get your flow. So it's very, very sensitive to cross-sectional area of your suction line.
So don't just add in a fuel filter because into an existing system. It's the way it was designed is absolutely critical. So understand what you're doing because a fuel filter, putting a small fuel filter in here, you're creating a massive, massive pressure drop.
Yeah, we have an example of a 10 that lives 2 hangars down. They went for the and air filter where they had 2 half-size filters in the wing roots or near the wing roots. And of course, again, half the area, 4 times the velocity, 4 times the pressure drop because it's double the velocity. 2 squared is 4, so 4 times the pressure drop. So it's all very well and good when you're sucking from both tanks, but as soon as you go to one tank, suddenly all the flow has got to come from one tank at half the size filter. They had problems. They had issues with losing power climbing out of Margate. So it's just, don't do silly things. If Vans tells you to use the filter that they recommend, stick with it.
I think that's it from us. Hopefully, we'll take some questions. But what we're going to do, to come and have a look at the graphs, to show you the graphs with the way the thing's projecting, unfortunately, you can't see the detail that is needed. But we're going to be here. Come and have a chat with us if you're interested to really see what's going on with your fuel system. We find it fascinating. And actually test flying that thing has been really, really interesting.
Avgas for everybody. Is a point to go Avgas for
Listen, Phil, you put the pumps in my aeroplane out there and they're both at the wing roof. And I've only run on Mogas, but I've never had it else.
2012.
Cool. Okay, thanks guys. That's basically it. I think you guys are going to do some experiments.
Yeah, if you want to come and see all this stuff,
Very
we can show
interesting.
you properly.
Yeah. Just leave my dop alone here, please.
I've got the
Get the loaf on the way back. Yeah, cool. Okay, and thanks, and we'll see you all at the next meeting, hopefully February at the auditorium. Thanks, guys.
Okay.